Welcome back everyone to our calc series. Today in session 4C, we'll be covering linearization and concavity. Now concavity is a topic from chapter 5 where we'll be talking even more about derivatives. And we're just going to talk about this briefly today because we're going to need it to understand something about linearization. And this topic will be covered again in chapter 5. Covered again. Okay, so linearization is a way to use derivatives to estimate the value of a function given a point nearby. So the idea is to estimate function value when given a point of proximity, right? So you're given a point nearby and you want to find another point. And to do this, we need to be given what f of a is. So we need to be given the function at a, right? And we want to have, we also need to have the derivative at a. So we need f of a and f prime of a and a, right? So this is what we need. So we need to get this point. We need to know its f value. So we have a. We need to know its f value, and we need to know its derivative, or f prime value. Okay, so now we want to have an estimate at x. And so here, let's say this f is this red line, right? And we want to estimate the value of f of x. So this is the real value. And linearization means that we use a linear tangent line to approximate the value. So what we're going to do is we're going to write out the equation of this tangent line, and we're going to call that this tangent line L of x. So what we can do is we can use point slope form. This L of x passes through a f of a, and it has a slope of f prime of a because the tangent line at point A is exactly equal to the derivative at A. So then we have Lx minus f of A is equal to f prime of A times x minus A. This would give us L of x is equal to f prime A times x minus A plus f of A. Oops. Plus f of A. Okay, so this is our tangent line right over here. And then we can just simply use this as our approximation. So as a result, if we look at this graphically, we use this tangent line, and we basically took the point x on this tangent line, and that is right over here. So if it's close enough, then this approximation is indeed good enough. So just to sum up the concept, linearization is basically you're given a point and you take the linear tangent line, the tangent line at that point, and you use this tangent line to approximate a nearby value and thereby giving an estimate. So this is the idea of linearization. And we're going to take a look at this example right over here. So we're going to linearize the function f of x equals x squared given the information at x equals 2. So here we have the function x squared, and we are given x equals 2. So this is obviously 4, and we want to estimate for x equals 3. Now, at this point, you might have noticed for this function here, it is really obvious what f of 3 is. F of 3 obviously is 9, and that can be obtained really easily. But in some cases, it is not so easy, or you don't know what the value of f is at that point. At least maybe it's not so easy to calculate, or maybe you're not given the function at over that interval. So then you would need linearization. And this is basically an example to show you how linearization might over or underestimate. So here we're going to take the tangent line. So if you just look at this this format over here, we can apply it to this f of x equals x squared. So f prime of x equals 2x. And at x equals 2, we would get L of x equals f prime of 2, x of 2 plus f of 2. F of x is approximately equal to this. So on an AP exam, you might just want to write this form right over here. And then you can keep on evaluating. So f prime 2 is just 4, x minus 2 plus f of 2, and that's 4. This is 4x minus 4. Okay, so this is our tangent line. And then we can just plug in for x equals 3. So f of 3 is approximately L of 3, and that is equal to 4 times 3 minus 4. That is equal to 8. So our approximation is 8, which is 1 less than the actual value for f of 3. So this here is an underestimate. Right? This is what we call an underestimate. An underestimate is when your predicted value or your estimate is less than the actual value, right? So here, 8 was less than 9, so it was an underestimate. Underestimate. Vice versa, if you have overestimation, then it is because the estimation is greater than the actual. Now, a few years ago, so like at least 5 years ago, the AP was testing a certain form of linearization. So like they would ask you to first linearize something, and then they would ask you if it's an under or over. But now if you take a look at the CED, this is not exactly part of it, but knowing if it's under or over is still very helpful. So we're still gonna, so this is why we're gonna cover concavity here, because concavity is what helps us understand if it's over or underestimate more quickly. Now, in the recent years, they're doing under and overestimate for integrals, so they would consider a Riemann sum, but we'll get to that in chapter 6. Okay, so concavity describes how the derivative changes. So you can sort of understand this as the derivative of the derivative, right? Because changing means a sort of derivative, right? So it's sort of the derivative of the derivative. And if you're thinking that, you're already on the right track. So if f prime is increasing over an open interval, so let's look at figure 8 right over here, then f prime starts out very flat, so it's like, let's say 0, and slowly it grows and grows and becomes very large. And so this is a situation where f prime is increasing over an open interval. Now, this is what we call concave up. So f prime increases means concave up. And because of this, linearization gives an underestimate. Linearization gives an underestimate. So this is actually really intuitive. So if you pick a point here and you take a tangent line, this tangent line is always below the graph. This is because tangent line is below graph. Now notice, there is something very important here, and it is, let's say your A is here and your X is, let's say here, then the open interval should just simply be A and X. Like this, or something that includes this interval. So it needs to be over the entire interval between A and X. It can't just be concave up like at a small spot and then like do something else later. So this is very important. So like if you need to have a consistently concave up function that at least encompasses A and X. So something like this or something like this. It needs the concave up interval needs to include A and X. Otherwise, let's just give a counterexample. We might have, let's say, this, like this, or actually like this. So here we have a concave up interval, but the linearization would give a clear overestimate, right? So like here we would have an overestimate. But there is a concave up region. So this is why it's important to have concave up all along, right? Then on the other hand, if f prime is decreasing over an open interval, then it is concave down. So this makes a lot of sense. So concave down like this, concave up like this. So then if we were to consider this even more, you would notice that this has to do with the second derivative. So specifically, if the second derivative is greater than 0, then that means f of prime is increasing. And that would mean it is concave up. If f prime prime is less than 0, then f prime decreases, and then it is concave down. So these are all related to each other. So f prime prime greater than 0 would directly imply concave up. F prime prime less than 0 would directly imply concave down. Now, if we were to evaluate or consider this for the problem that we just had right over here, then we would find that, so this f of x equals x squared, then f prime prime x would just be 2. And this is always greater than 0 for all x from negative infinity to positive infinity for all real numbers. So then we want to estimate over 2 to 3. So we want to get from 2 to 3. And so clearly on this whole interval, we have concave up. So therefore, because it is concave up, we have an underestimate. So this is how you could tell if a function, if a linearization gives an over or underestimate without doing a lot of computation. So you just have to know about f prime prime or f prime. So you just have to know about this or this, and that is enough to tell if it's concave up or down. Now, before we move on to a practice question, I would like to note that in the CED for the more recent exams, you are only required to know linearization, and that sometimes it's an underestimate, sometimes an overestimate. You're not exactly or explicitly told to know about concavity at this point. So you're not expected to tell immediately if it's under or over. You just need to have the concept that sometimes it's under, sometimes it's over, and sort of have an intuition. But it's always still good to know about concavity and to be able to have another way. So here we have an FRQ problem from 2014. You should be able to do subproblems A and B, but not C, because that would involve integrals. And for D, we have the linear approximation to A, LT, to predict the time at which there will be 0.5 pounds of grass clippings. So LT is equal to A prime of, so notice the linear approximation to A at t equals 30 means that our A is sort of 30, right? Our A, like the reference point that we were talking about. So this linear approximation then we can just write as A prime at 30 times t minus 30 plus A at 30. So this is our linear approximation, and we want this to be 0.5. Then we can easily solve t, right? Okay, so then just as a bonus here, we want to know if this linear approximation is an over or underestimate. Again, as you can see, this AP problem did not ask about over or underestimate, and that is because it's simply not in the CED. So you could choose not to know about concavity at this point, but later you would have to know anyway for other purposes. And here, one good way to deal with this is just simply to take a look at A prime prime t. And so before that, we're first going to take a look at A prime t. A prime t is equal to, if you paid attention to the derivative of an a to the x exponent, then you would know that the derivative of this would be the constant here, obviously, times, so you would take the loin of the base times the thing itself, right? And you can derive all this from the chain rule and the derivative for e to the x. If not, you can check our video back there again. And we notice that this constant right over here is less than 0 because loin is a function that looks like this, right? And it hits the 0 at 1. So anything less than 1 would give negative. right? So a prime prime of t is just equal to the derivative of this. So it would take this again, and you would end up with another factor of ln 0.31, like this. And because this is negative and this is also negative, we end up with something positive, right? So this is always positive, right? An exponent with a positive base. This is positive, and we have two negatives. So this whole thing will be greater than 0, and therefore it is concave up. And so this would be an underestimate. And that is it for today's video. We talked about linearization. Thank you.